Well, hello there. This is Aurora with Supercharged. Oh, I'm sorry. Let me try that again. This is Aurora with Central Coast Astronomical Society. Today we have a very special guest. We are going to learn about galaxies. I know during the month of March, we spent a whole month just studying all we could about the night sky. We had 22 live events, and this is one event that I thought because it was so special, we wanted to make sure it didn't get lost in the jumble last month. So I'm super excited that you are going to be joining me today. And one of the special guests that I'm going to be introducing is Dr. Xinnan Du, and she is with the Outreach and Engagement Manager at Kavli. Gonna mispronounce that. You want to help me? Kavli Institute. I totally did that wrong.
You almost got it. It's actually the Kavli Institute for Particle Astrophysics and Cosmology. It's a super long name.
It is a super long name. Now, you were inspired by one of Stephen Hawking's books. Is that correct? In high school?
Yes. Yeah.
Uh-huh.
And so I was actually really interested in physics at that point. And I actually read the illustrated version, not the full version, of one of Hawking's book, A Brief History of Time. Yeah. I did not enter a thing, but I was really intrigued by all these images and very fascinating phenomenon.
Yes.
So I was like, wow, I really love astrophysics. I really want to figure things out. So that's how I initially got started with astronomy.
Oh, that's wonderful. And where do you work now? I mean, I know you do a lot of different projects right now, but if you could pick a couple to mention, just so people know what you're up to.
Oh, yeah, of course. So I actually have a slide on my presentation, but I currently work at KIPAC, the Kavli Institute. So that is at Stanford University and also at the SLAC National Lab. So this is actually, as you can see, one of the Kavli buildings at SLAC. And before that, so I got my PhD from UCLA in astronomy. After that, I moved to UC Riverside for 3 years, also doing research, managing education programs, and also doing outreach.
Wow.
Yeah, that's so wonderful. I have spent most of my time in the US in Southern California, and I just moved here last December.
Oh, wow. Well, welcome.
Thank you.
Well, what are we going to get to talk about today?
My presentation is actually two parts. One is just a little bit about my journey into astronomy and also into outreach, and maybe tiny little bit of messages about what I think of this kind of career path. But mainly and scientifically, we're going to talk about galaxy breathing.
Oh, that's wonderful. Now, that's such an unusual concept, like galaxies breathing. Like, those are not two words I put together.
I know, right? Yeah, that's also what I thought when I started doing research on this topic. I'm like, what? But the more I think about it, the more I just find it fascinating. Yeah. And I also really enjoy giving this kind of presentations or just simple or very informal conversations with students and the general public. So this is what I enjoy doing.
Oh, that's great. So students, just as a reminder, for those of you on Zoom, you want to direct your questions to me. Dr. Du will not be able to see your questions, even if you submit them to her. So you want to submit them to me because we're broadcasting on multiple channels. So I will get those questions and let her know when it's time for the question and answer part. But if you have questions anytime, feel free to type them in to me, to Aurora, and I'll make sure that she gets those questions. All right, are you ready to take it away?
Yes, let me start sharing my screen.
Absolutely.
Wonderful. Okay. So again, hello everyone. My name is Xinnan Du. I am the Outreach and Engagement Manager at the Kavli Institute for Particle Astrophysics and Cosmology. And for short, it's called KIPAC. I am, as I said, very new into my current role, but I have been studying in the field of astronomy for the past 12 years or so. So very excited to be meeting all of you virtually today. And I very much look forward to the interview / discussion afterwards. So A little bit about myself. I actually did my K through 12 education in Beijing, China. That's where I was born and raised up. And I first got interested in astronomy as Aura just asked, actually just because of this book. And I tried my best to find, I think is the exact version of the book cover. And as you can see, it's a translated version and also illustrated. So I was pretty good at physics. And that was what initially motivated me to actually go into college to study astronomy. And I did that in Nanjing University. After graduating, I went to grad school to get my PhD at UCLA. And I moved to UC Riverside, which I will also talk a little bit more about, doing outreach and also managing programs there. And I just moved to KIPAC, Stanford, a few months ago. So actually in high school, I was not only interested in astronomy, but also other subjects. For example, I was also really good at biology and also very intrigued by psychology. So I was actually debating between psychology or neuroscience and astrophysics at that point. It was not a very clear answer to me read at the beginning. So in my very naive understanding back then, I thought, well, biology is, very fact-based. As long as I remember some of the facts, I'm all good to go. Well, so of course, now I figured it's not the case now. But at that point, I thought, well, physics, I feel that's more challenging, that I have to understand how things work. So that's how, I chose that, because I could, constantly getting challenged and try my best to learn. And another thing is, I still think that way. That is, nature or basic sciences, they are simpler to study because they are ultimate principles that governs the world or the universe, which are, physical laws. But when you study human beings, it's the most complex system you could ever encounter, because you could never predict how people behave, what they think. But still, even right now, I am still interested in biology and psychology. And I even think, well, if one day astronomy doesn't work out, I might just go back to school and study those subjects.
That's a great idea.
Yeah, I mean, you never know, right? So, and I actually took a psychology class in undergrad, and I loved it. It was cognitive psychology. So at least I had some coursework there. So in college, I actually took a lot of advanced classes in math, physics, and also astronomy in the first couple of years. I had the opportunity to actually start a small research project. So my first project, it was almost like this. It was very math heavy, that I took a quarter to try to finish a very high level paper that gives an overview of the field. I remember it was like 50 pages full of this kind of equations that I did not understand. And I was getting very upset and thought, well, maybe astronomy was just not for me. But in one summer of, it was actually the summer of my junior year, that I got to do a 10-week summer research internship at UCLA. And that was the first time that I started doing research with observational data. So this was almost very similar to what I was dealing with. I was constantly looking at images of galaxies, and I was gathering data that shows how bright they are when being looked at in different colors. So I really enjoy, at least, just looking at images of stars and galaxies. And even though the work was a little bit repetitive, I was still very much enjoy that. So that was the point where I thought, well, maybe I could also try to explore research a little bit more. And that's how I applied for graduate school and determined that I would just be studying galaxies. So, of course, as a graduate student, and I know grad school may be a little bit far down the road for all of you, but I was doing a lot of research, of course, all related to galaxies. But at the same time, I got really interested into astronomy education and specifically outreach, which means, we conducted this kind of either activities or presentations, events that are learning opportunities, but outside of the classroom. So the first volunteering opportunity that I got in grad school, I still remember it very clearly, was actually an event at a local elementary school. So they were looking for a bilingual speaker, both in English and Mandarin, to teach about planets in the solar system. So I was one of the few that were even capable of doing that. So I signed myself up. And I really, really enjoyed talking to those students in both languages. I felt, there was this initial or an instant click when we spoke the same languages. So that was pretty much what initially got me into this outreach journey. And after being a volunteer for a little bit of while, I also started leading the team, which is also 3 or 4 graduate students at UCLA, to visit local K-12 schools to do more of this kind of educational sessions. After getting into after I graduated, so I arrived at UC Riverside, where I not only did research, but also was given the opportunity to manage some educational programs established by my supervisor, but also funded by NASA. So one of those was actually providing learning opportunities for high school students and teachers, where I managed to coordinate and also plan a student summer academy where high school students take summer session courses at UCR and get credits. There are also teachers training programs in data science. There are also capstone projects in research for high school students. And we also organized, science fairs at local high schools. And this is actually a group photo, me with only a subset of volunteers when we first run this at Patriot High School in 2019. So it was very fun, and I enjoyed that part a lot. And of course, aside from actually coordinating programs, I was also very passionate about outreach, and I still am. So I voluntarily signed myself up to organize more events, not only for my supervisor's programs, but also on behalf of the department. So UCR Physics and Astronomy. And these are some of the events that we organized. They were all before or in 2019, before the pandemic. And aside from these, we also had, telescope viewings, public lectures, large scale events, K-12 camp sessions, as well as classroom and school visits. So again, that part was my favorite part, actually getting into, not only organizing these events, but talking to students face to face, well, almost like what I'm doing now, except that it's virtual. So COVID was absolutely a very difficult time for all of us. And for those who wanted to get connected to students and also schools, we just had to find better ways and also new ways. So I actually created multiple online programs where almost all the in-person programs had their virtual counterpart. So those include virtual stargazing, again, public lectures. We also had events for sci-fi related materials, and also K through 12 presentations. So keeping the virtual participation as an option is also what I'm hoping to do now at KIPAC and Stanford, since during the pandemic, we already know that we have the resources and capability to reach out to a much larger community. So we don't really have to just limit ourselves to serving those around us. So that's also why I am super excited that I get to talk to you today, even over Zoom, but we could still interact in this fascinating way. So you may ask, well, is doing education or outreach a very typical career path, especially after getting a PhD? Is that what you signed up to do? Well, my answer is absolutely not. So I didn't even know doing outreach or this kind of informal education would even be a possibility when I started doing it. But over the years, especially in graduate school, I really found that I was interested more in doing outreach than doing research. I really enjoy presenting fun science to students and to the general public than actually doing research to make scientific discoveries. So, that's how I got here. Well, I know if you're watching this right now, you're at least just a tiny little bit interested in STEM or possibly getting a degree or a career in STEM. So many people think that, for STEM professionals, you basically just take so many years of school, so you do research, and finally you become a professor and teach in a university. That's also what I thought when I first got into this field. But as time passes by, I also discovered that there are just so many other science-related careers that you could possibly take, and you are still contributing to the discoveries that we're making every day. So you could teach in a school or doing this kind of informal education. You could write about science. You could make policies that advance science, or working with to actually give money to fund those research projects. Or if you want to actually turn the science into a product everybody uses every day, then industry is also available. So science cannot progress without all these professions. And you don't have to really decide what you want to do with your STEM degree right now. I would just encourage you to try everything, take baby steps, and see what you find that you're most interested about and what you're also good at. So I guess that's my little story about my career path. Or should I take questions now, or should I go ahead?
Why don't you go ahead with the astronomy part? You've got a lot of astronomy questions, but I thought maybe if you present astronomy first, maybe that'll answer some of the questions. Where are we? Questions that had come in. So you got a lot of kids that are excited and are taking notes on how to be a scientist.
Well, that's great. And this is actually also the fun part. So galaxy breathing is what I did on research in graduate school, and also even after I got to UC Riverside. So today I will be presenting some of the most fascinating, at least I think they're fascinating, facts. This is going to be a very interactive one, and I want you all to participate by typing in the chat if possible. So the first question for you is, what do you think we can find in a galaxy? Anything that you can think about.
Okay, and students, you can write to me, or you can write, well, I don't know if she'll get it, but you can write to me if you'd like, and I can read some out. I've got a collection of stars, black holes, planets, solar systems, more stars, space dust, gas and dust, same thing as under my bed. I think you mean dust bunnies. Stars, collections of stars, nebulae, water, all the elements on the periodic table.
Wow.
Okay, so there you go.
Oh my gosh. Okay, well, you guys are much more advanced than I originally think, but this is great. So as you all mentioned, we have stars. There are clusters of stars, right? There are black holes and also supermassive black holes. Typically, we found at the center of a galaxy. And finally, this is what I will be talking about today. That is gas. So, well, gas is not something that you would immediately think about when thinking about a galaxy. But as you can see after my presentation, it's actually what fuels a galaxy to be alive. So I guess for this one, I also want to get a yes or no vote, but I guess given your levels, you probably all know what the answer would be.
Let's
see.
Do
you think stars have anything to do with gas? Are they just occupying the same spatial location, or they actually interact with each other?
You have not one no over here, by the way. They're all yes, yes, wow, yes, 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 yes. Stars are made out of gas. Of course. Yes. Yes, yes, yes. Okay.
Wonderful. All right. So I guess I will just not keep that as as a question to be answered later. Yes. And this is also how we are going to start this presentation. I know some of you already know this fun fact, but just as a recap, so for stars, they actually form in very cold and dense clouds of hydrogen. So even if we have a gaseous cloud, if it's hot enough, it wouldn't be dense enough to actually gravitationally collapse to form stars. So when clouds collapse, they actually become hotter and hotter as it gets compressed, right? They grow in mass, and at the center, the pressure and temperature, it becomes higher and higher. So at some point, the center is of high enough temperature to actually ignite hydrogen. And that is about 13 million degrees. It's extremely hot. And when a star is formed inside, we could see some of these stellar nurseries that we would typically observe in amateur astronomy. For example, the Orion Nebula, we could see them typically in the fall or in the winter. It's a very well-known region where there are active star formation. Or we also have these pillars of creation in the Eagle Nebula. And you can see these are immense columns of cold gas, and the newborn, very massive young stars are actually embedded inside. So for stars, they actually spend about 90% of their lifetime being structurally stable, because there is the gravity that tries to pull it inwards, and there's also the pressure that comes from the nuclear fusion from the center. So these two forces, they balance out, and during this stage, the star will be giving a pretty stable energy output. At the center is actually burning hydrogen to form helium. So for our sun, this process, well, I guess not only for our sun, this whole stage of it being stable is called the main sequence. And for our sun, the main sequence lifetime is about 10 billion years. And do we already know how old our sun is?
Let's see if we have some answers here for you. Oh, it usually takes a minute here. No. Not really.
Not really?
Not sure. Oh, you got a lot of zeros coming in now. Sort of, a lot.
Yes, a lot. I like that answer.
You better answer this one directly.
Yeah, so according to our current understanding of stellar structures, our sun is about 5 billion years old. And so it can live for another 5 billion years. And of course, something really bad would happen. It would really puff up and Earth would be engulfed into the sun, but we don't have to worry about that because it's not happening in our lifetime. At least I always comfort myself that way. So after the helium, after hydrogen has run out in the core of a very massive star, you are left with a bunch of helium, right? And this is where sort of magic happens. And I would actually introduce you to this video that is posted by NASA. Let me just make sure that I have my computer sound shared. Okay, great.
In this demonstration, you'll use balls of clay to explore how stars fuse elements inside their cores. Each different color represents a different element. Here, pink represents hydrogen, blue is helium, purple is carbon, orange is oxygen, and this tennis ball is neon. We'll start with hydrogen, just like you've got in the center of a young star. The inside of a star is hot and dense, and all of these hydrogen atoms keep bumping together. Often, some of them will stick together. This is called fusion. So we squish together 4 pink balls representing hydrogen, and these form a new element, helium, represented by the blue clay. The sun's been doing this for nearly 5 billion years. Eventually, the hydrogen in the center of the star runs low, and we've mostly got a lot of helium jostling together instead. When hydrogen fusion stops, the star is no longer in equilibrium, and the core shrinks down. But this makes things even hotter, so the star can start to fuse helium into carbon. So we squish together 3 blue helium atoms to make 1 purple carbon atom. In the sun, this is where things will end once the helium runs low. But if a star is much bigger than the sun, the core will shrink again, and it'll get even hotter at the center. Now the star can fuse together a carbon and a helium atom, creating oxygen. So we'll squish a blue helium atom and a purple carbon atom, and that turns into 1 orange oxygen atom. You can imagine what happens when carbon runs low and fusion stops once more. The core shrinks, things get hotter, and new fusion can begin again. Helium and oxygen start to fuse into neon. So we squish a blue helium atom and an orange oxygen atom, and swap that out for a tennis ball that represents neon. Depending on the size of the star, this process can continue through the periodic table up to the point where iron is formed. But to fuse iron, you need to input energy.
Okay, I'm gonna stop here so it doesn't actually spoil what I'll
That was a lot of information.
It is, and I found this kind of visualization really helps to actually get to comprehend what's happening inside of a star. So now we know nuclear fusion can goes on, and depending on the initial mass and size of the star, for really massive stars, it can fuse iron. Okay, I don't want this to play again. Cool. And if we just take a quick look at the periodic table, we can see that at least all these elements, they are primarily created inside of a star. And just a quick reminder, when the universe was first created, right, there were only hydrogen and a little bit of helium. So now we have this whole periodic table. And of course, aside from those that are, man-made elements, the other elements, they were all created somewhere, many of those inside of star in the universe. So when fusion stops at iron, there is basically no radiation pressure going outwards, just because, as the video quickly mentioned, to fuse iron, it actually needs to take more energy from outside than giving out energy. And that process, it just doesn't happen naturally. So what it does to the star is when iron is formed at the center of the star and it cannot keep burning, then gravity would momentarily win. It would just constantly try to compress the core further and further. And remember, just because fusion was almost stopping at that time, there is no pressure because of the diffusion. going outwards to balance this gravitational collapse. So it's almost a runaway effect that all the envelope where you have hydrogen, helium, carbon, oxygen, neon, it would just try to free fall onto this iron core as the core is shrinking. And whenever that free fall is getting stopped at the surface of the iron core, because it was free falling at a really high speed, it just automatically got bounced back, and that was what formed would form a supernova explosion. So both of these, this is actually a simulation trying to visualize what a supernova explosion would look like, and this one is actually a Crab nebula that was a supernova remnant. So all these filaments, or like colored patches you would see, they're actually very hot, tenuous, and ionized gas. And when a star dies in a very violent way, massive stars, what we have in the center would just be a neutron star or a black hole. So of course, now we're coming back to this question, and all of you already answered yes. So that was wonderful. Stars form from gas, and they can also expel gas. So one thing I found really interesting about supernova explosion is that galaxies, well, these supernova explosions are actually very energetic, that sometimes it can actually eject the gas inside of the galaxy outside of it. And remember, the gas that gets ejected, they also contain all the heavy elements that were formed inside of a core of the star, right? So when these kind of explosions happens, the ejected gas is actually more polluted, or we could say, it contains more heavy elements. They are more chemically enriched. And this is actually not a fake picture. It's one of the galaxies that we observe to have such very powerful gas flowing outside of the galaxy. It's also a disk galaxy right here. And all these gas you see almost in cones, they are very hot X-ray emitting gas getting kicked out of the galaxy.
We actually took a look at this one, I think it was week 31 students, when we looked at M81 and M82.
Yeah.
Yep. So yeah, we talked about this one quite a bit. So please go ahead.
Oh, awesome. Okay, so this is actually M82. It's known as a starburst galaxy because the star formation actually drives this kind of gas outflows. And aside from ejecting gas, galaxies can also accrete cold streams of gas from the intergalactic medium. And intergalactic medium is also gas, but they are located in between galaxies instead of inside of galaxy. So when they create these kind of fresh cold streams, these gas contains a lot less heavy elements. So they're mainly just hydrogen and helium, a very primordial gas as you would expect from an early universe. So, well, we don't have to do this on Zoom, but if you were to draw galaxy outflows and inflows based on the story that I just told you, how would you draw it? And this is, a galaxy that we're looking edge on, right, instead of face on. So if you were to draw it, you could draw on a piece of paper that you have, and just thinking about, there are gas flowing out, there are also gas flowing in, and how would you represent them, using arrows.
And you've got some kids asking about this particular picture, and they're wondering, is it a real picture? And you've got some guesses as to what it is.
Oh, this is a real picture of a galaxy, but I I don't actually know which one it is.
Oh, you don't know? Okay, no problem.
Yeah, this is supposed to be, representative of a disk galaxy. I'm sorry, but
no, it's okay.
These stars, they look a little bit Photoshop to me, but I mean, this galaxy is very, very real.
Yeah. Okay, great.
Cool. And so if, based on what the story that I just told, so you would draw some polluted outflows, right? Outside of the disk, almost perpendicular, getting ejected out. And you would also have those, cold gas getting accreted onto the disk to actually replenish the gas components. And one thing that's very interesting is that we do not only have these two modes. There could also be gas that was, initially ejected, but not at a high enough speed that would just escape the galaxy all at once. So if they were ejected not super powerfully, these kind of gas would also fall back, and again, to become recycled and become a part of this galaxy again. So we actually call this phenomenon the galactic fountain, because it's just like, fountain where you have recycled water. And for this kind of recycled gas, of course, it's still polluted and the galaxy is not getting rid of them. So why are we talking about galaxy breathing? And I actually want to compare the big picture we just talked about with human respiration. So we know for human being, we breathe in fresh air, which typically means very low in the content of carbon dioxide, right? But it's also not all oxygen. There's a lot of nitrogen. And it goes through our lungs. We need to metabolize. And when we breathe out in our exhale, we have a lot of the metabolic waste, including carbon dioxide, that we breathe out. So this kind of, breathing in fresh air, having the metabolism and breathing out more polluted air is also the same with galaxies. So remember, galaxies, they breathe in relatively fresh gas that's mainly made of hydrogen and helium. They also breathe out chemically polluted or enriched gas that contains, a lot of these heavy elements because of supernova explosions. So what is galactic metabolism here? It's actually star formation. So depending on the initial mass and size of a star, they actually would go through different evolutionary paths, right? And probably a lot of you have already known this, but the gas is what initially fuels star formation, and star formation is also the driving force for this exhale, for the outflow gas that we're observing. So one other reason that I'm comparing these two is not only because of this similarity in terms of inhale and exhale, but also when we're considering a person as being alive, we know that it's constantly breathing, right? They're constantly breathing and they're also metabolizing. And it's the same when we're also saying, well, a galaxy is actively forming stars, and we consider it as, like very energetic and has a bright future of some sort. But when we're considering a dying galaxy, if not completely dead, it's actually something, or a galaxy system that already runs out of available gas to form future stars. So, if no more stars are forming in the future, then this galaxy would basically just evolve and wait for all the existing stars to die, right? So it almost has, no exciting future, unless at some point in the future, there are, again, accretion of cold gas into the galaxy that would actually revive it. Otherwise, it would just gonna, keep dying. And typically what we see as a dying or dead galaxy is this kind of, like reddish, very gigantic elliptical galaxy. And fun fact, in about 4 billion years, the Milky Way galaxy will actually be colliding with the Andromeda galaxy. And the end product would actually be an elliptical galaxy. So after we merge with another galaxy, this is our ultimate future. So I guess I'll stop here and take any questions.
Oh boy, where do I start? Okay, so first of all, I'm getting lots of thank you. This is great. I'm so excited for your class. Okay, they are wondering, how do you take these pictures that we're seeing? That's an interesting question to start with.
Oh, it is a very great question. So I didn't, should I keep sharing or should I stop?
Please do.
Okay, well, first, I didn't take them myself, but there are several ways. For like these really high resolution pictures, so typically space telescopes take them. Like Hubble has taken a lot of pretty pictures. But for like Andromeda galaxy or some of the gas nebulae or supernova remnants, if you have a pretty decent portable telescope and with a good camera, you could also do astrophotography, and you're able to actually reveal a lot of the details of those objects.
Nice. Okay, great. Here, I'll make it so they can see us both. All right, so students, how are you doing? I know she covered a lot. So good. Okay, I see a lot of happy smiles and thumbs up. Okay, so all right, questions that are coming in. Do you have any news about the James Webb Telescope?
Oh, great question. Yes. So I guess the James Webb, the last time I heard is that it's actually doing all the scientific calibrations. So, after we launched it, there were so many steps that it would have to, test and make sure that it is ready to take scientific data in space. So I think now the scientific calibration, they are all running as planned, and we are probably expecting some real scientific data by the end of the year.
That's awesome. That is so exciting to think about what's going to be happening.
I know.
Yeah. Okay. Other questions? How? Let's see. How did you decide? I think what they're trying to ask is, how did you decide on astronomy? Was it the book you read, or was it something else? I think that's the question they're trying to ask.
Yeah. So I initially decided on astronomy because of, myself being pretty good at physics, and also the book. The book was a big driver. What really kept me continuing was that I enjoyed learning every bit of it in undergraduate school. And I also enjoyed doing research, and especially, doing research related to those pretty big pictures.
You've got students asking for the link to the video. They want to watch the rest of it.
Oh, of course. I can actually share that with you.
That'd be great. Okay, perfect.
Yeah.
Okay, great. Okay, I'm trying to monitor lots of different channels here. Okay, so let me jump over to this channel. And okay, so one of the questions was, how can we tell if the images are true color or if they are just colored by scientists for information reasons?
Oh, that's a great question.
Yeah.
I wouldn't be able to tell without actually, a proper caption. Sometimes I guess because, even in the optical wavelengths, we could still have, at least 3 different colors, right, to make those color composites. But in terms of like how they would represent, say, like ultraviolet or infrared, or sometimes even like radio wave, using optical light to enhance the visual effect, you would actually have to read the caption.
Yes.
Because I don't think there are some like uniform principle as to how to do that.
Okay, great. That kind of leads into this other question. On a daily basis, what kind of instruments do you get to work with?
Oh, great question. For my research, I primarily used, telescopes in Hawaii. So there's the KIPAC telescope. It has a 10 meter, a mirror with a 10-meter diameter. So that's where I got most of the data for my research projects taken. And of course, I also used data from the Hubble Space Telescope.
Okay, great. Okay, this one's cute. So do you ever get to actually look through a telescope when you do your work, or do computers do it for you?
Oh, this is a wonderful one. I don't really look through in terms of through an eyepiece,
right?
Because the KIPAC telescope, it's so huge, it doesn't really have an eyepiece. So what I would do is I actually use computers to remotely control that telescope in Hawaii and tell it where to point it, how long I want to look at a specific field, and then take the data directly, using all digital systems, not necessarily, having all those photons directly hitting my retina.
Right. Okay, nice. I wonder, do you have a picture of the Keck telescope that you could share?
I could definitely search for one.
Okay, yeah.
Yeah.
Have you do that. Let me answer a couple of the questions that have been coming in. So yes, this goes with last month's content where we talked about astronomy. We just happened to have a lot going on. So that's why we're in the middle of turning all of our students into pilots. So we've been doing aviation. So one of the few of the questions were, how come we're talking about galaxies? We're not going to be able to fly there. So this is for last month. So this is based on astronomy that we were doing last month, not aviation. So
yeah.
Okay.
I would actually love to fly to other galaxies.
Wouldn't that be something?
I would love to. I don't think I would be able to, or we would be able to very soon, just because the huge distance between the galaxies. We were talking about the closest star aside from our sun, right? That's located at 4.3 light years, and we cannot even travel at the speed of light.
Not even close.
Not even close. So even to Mars, right, it would take us months to get there.
Yeah.
And we're talking about, traveling to another galaxy. There were only two ways, if it were to happen, that I could see it happen. One is there are some ways that we could actually infinitely prolong our lifetime, right? Or freeze ourselves and then wake up in the future.
Yes.
The second one would be, for some reason, that we actually discover some loopholes in, relativity that would allow us to, even not travel at speed of light, but maybe close to the speed of light, like half of it.
Yeah.
But still, that would take us, I would say, millions of years.
Long time.
Long
time.
So, I don't think it would happen in my lifetime. Unfortunately.
No, unfortunately. I know, it's such a bummer. I wish we would have been born in the time where there were spaceships zooming around the galaxy, but not this time around.
No, this time around. And I do have some pictures of the Keck telescope.
Oh, that'd be great. Let me make you full screen, and then I have maybe 3 or 4 more questions.
Oh, of course, yeah. So there are all different kinds of pictures. So KIPAC actually has 2 domes. So KIPAC 1 and KIPAC 2. This is on the top of Mauna Kea. That is a mountain in Hawaii. And when it is actually working, you would see something like this. I mean, this might also be a little bit, photoshopped, but the KIPAC telescope, they would actually shoot out lasers to help with observations. Yeah, and that is for, to correct the turbulence in the atmosphere. Otherwise, you would have very shaky images, right? It's like stars twinkle, and you don't want that when you're actually take data. And then, so this is what the telescope actually looks like inside. This is the primary mirror.
Yeah, do you guys see all the hexagons in there? Yeah, so it's not one giant mirror. How many mirrors are in there?
Good question. I think they are like 20 something.
Yeah, I think you're right. Okay.
Yeah.
Okay. Nice. One of the questions was how could there be other elements out there we don't know in other bigger stars or other galaxies? It's an interesting question.
Great question. Well, I would say it's possible, but it's not likely.
Okay.
Because, as we go down the periodic table, right, all the heaviest elements, they're almost all man-made. And whenever we know, well, according to our current understanding, right, whenever we know whether we're missing an element or not is to actually see whether there are gaps in that periodic table. Because, for example, we know there's nothing missing because we have discovered almost all the elements that are adjacent in atomic numbers, at least, below 90, with, not the atomic number, right?
Right.
So at least we're not missing anything there. We might be missing something that's heavier, but I would assume that it's almost just going to be man-made, not inside of a star.
Right. And when you mean man-made, we don't mean that they dug it out of the earth and formed it and shaped it into something like a car. We don't mean man-made that way. Since you work at SLAC, you want to say what man-made means?
Right. Yeah. Okay. I should clarify. It's like, it's like we make them, in the laboratory, right? It's not like through a natural process that we directly discover somewhere.
Right.
Either on the Earth or in space.
Right. They're smacking things together really hard, really fast, and seeing if they can make a new atom.
Yeah.
Exactly.
They've been doing that, yes. For many decades.
Yes. Okay, great. Let's see. I just have a couple more. If you could go visit a galaxy, which one would you go to and why?
Oh, that's a good
I think
one.
that was from our rocket ship comment before.
Well, interestingly, even though I study galaxies, I don't actually know, their names that much because, when I study them, there's just an ID number label with each of them. It's almost like my patients, right?
Yeah.
But I don't even need to remember the name. But if I were to visit one, I would probably choose one that's in the local group, pretty close by to our Milky Way, but it's one of those, satellite galaxies that we call dwarf galaxies. They're much smaller compared to, disk galaxies like our Milky Way. But they are very interesting because, they could possibly present something or exhibit similar properties of a very young Milky Way back in the days. And there are just so many things that we don't really know about them. So it would be a completely different environment that I want to live in.
That's awesome. Okay, and here's one. Have we ever taken a sample from the sun or touched the sun? Hey, we used to be able to say no, but now...
Yes, but now we have been very, very close to the sun. So there are several solar probes, well, very, very close to the sun, but not physically touch. Very, very close to the sun. So there's the Parker Solar Probe, which we actually launched to study the properties of the sun and also space weather. I wanted to clarify that there's actually no solid surface of the sun, right?
Right.
So there's like really nothing to exactly touch. And the sun, it is a lot more than, just like gigantic fireball that we see because it's constantly driving these, what we call solar winds. Those are charged particles traveling at extremely high speeds, and they could easily impact the environment on Earth. So, we have been really, really close to the sun, but I don't think we would be able to actually touch it.
No, it's not like going up and touching the moon. It's very different.
Right. At least the moon is a solid object.
Yes. Oh, that's wonderful. Well, thank you so much. Did you have any last closing remarks you wanted to leave us with, or anything you wanted to share?
Oh, of course. I mentioned that at KIPAC, we're also trying to run different educational sessions. So if you don't mind, I can give a quick plug.
Go for it.
Of what's happening next.
Yeah, go for it.
Wonderful. Okay, so there are several opportunities that I figured might be of interest to our audience here. So one is we actually run virtually public lectures. The next one will be on May the 10th, talking about dark matter. So these public lectures are advertised to advanced middle schoolers and high schoolers and above, of course. But given your levels, I think it would be very appropriate, and you might actually enjoy it a lot.
Okay.
And don't worry, I will share all these flyers as well as the link to the NASA video, all with Aurora, to share with you later.
Yeah, and then I can send it out to everyone. So perfect.
Yes. Yeah.
Okay. Great.
Another virtual education session we're doing is actually called Astronomy Night. So those are going to be 2 nights in May, 1 hour each. And during those sessions, we'll be doing interactive activities over Zoom to learn about different fun concepts of astronomy. So it's going to be, very hands-on, and there might also be group discussions. And again, it's free, it's virtual if you want to sign up.
Great.
And finally, we are having this summer learning program, also virtual, for 3 weeks. It's for high school students to actually learn about computer programming, different subfields in physics, and also working with undergraduate and graduate students to solve physics problems using the computer skills that you learned in these sessions. So these are 3-week, again, over Zoom, but you'll get to, learn not only astrophysics, but different subfields of physics, and also computer programming, which is very, sort of like essential if you actually want to do research later. Mm-hmm. And one last thing, I'll stop share. For all of those who are actually in Northern California or pretty close to Stanford, we are also going to have a lunar eclipse viewing party on the Stanford campus.
Oh,
but,
wow.
But for all of you, you can do that all by yourself because you don't really need a telescope.
Right.
So it's going to be May the 15th. I know in Pacific time, the lunar eclipse will start from 8:30 p.m. And the moon will already be in eclipse when it rises from the horizon. Mm-hmm. But it's going to last for, at least an hour. So if you actually want to see a bloody moon, that would be a good opportunity. And if you actually, can join some of the local groups where they have a telescope, then you could even observe some of the details on the lunar surface, which would be very cool. So I will also share that information. And well, thank you, Aurora. That's exactly what I wanted to show.
Perfect. Okay, great. Yes, I'm good at running things behind the scenes.
This is wonderful.
Well, thank you so much for sharing your passion and your excitement. One of our goals is that everybody wants to be an astronomer. So
awesome.
That's what we want to inspire people. And during your talk, we had lots of students call in and listen to me. I'm so old school. We used to do this only on the phone. And so write in to let us know that they're so excited we're still doing astronomy, even though we're in another subject this month. So when will the eclipse happen? So I will put all of this detail in an email and it'll be sent out to you. So if you're on my mailing list, great. If you're not, take a look at centralcoastastronomy.org and we will make sure that you get the information that you need. Just go to our website and you can sign up. It's free. And we'll send you an email with all of these links and everything that you need. Okay. Well, thank you so much. I appreciate you spending time with us. And if students have questions, is it okay if I pass them on to you by email?
Of course, yeah. And
Okay.
feel free to share my email address
Okay, I will.
as well. Yeah. So if you have further questions, feel free to directly message me.
Excellent. Well, thank you so much. And I look forward to seeing you again in the future. And
Of course. Yeah. Well, thank you for having me. And
pleasure.
it was really nice meeting all of you.
Awesome. Well, thank you. All right. Bye-bye.